Hello everybody, my name is Hunter Ream and I'm going to be talking to you about Generating Functionology by Herbert Wilf. In particular, we're talking about section 2.3, the calculus of exponential generating functions. This is part 3 of a 3-part series where now we're going to be covering the last rule called Rule 3 prime. And it says if f is an exponential generating function for a sub n 0 to infinity, and g is another exponential generating function for a different sequence, let's call them b sub n's, then the product of these two generating functions generates the sequence of these sums. So n choose r, a sub r, b sub n minus r, from n equals 0 to infinity. And the reasoning, let's just note something. This one we can just do by hand. We can say, well, if we have the first one, let's say it goes from r equals 0 to infinity, and it's a sub r, x to the r, all over r factorial. And the next one, let's index by s. So b sub s, x to the s, all over s factorial. And if we multiply this out, we get that r, this is a lazy way of writing it. If we just multiply every single thing together, we can write this double sum as instead r comma s greater than 0 of just a r b s over r factorial s factorial x to the r plus s. That's just kind of a lazier way of writing it and just multiplying everything together. But we can actually group some of these terms together, right? We know that the terms, so let's instead, if we range over some n, well, at any fixed integer n, if we wanted to collect all of the like terms that are on x to the n, what are they going to look like? Well, they're going to look like the terms where this r and this s add up to n, right? But that r and s are the same as this r and s and the same as this r and s. So it's really just the fact that we need the r and the s to add up to n, and that will collect all the like terms. So the coefficient on x to the n will be the sum of all r and s, where r and s equal n, of a r b sub s r factorial s factorial. And so that's exactly how we collect the like terms. Because we know that if r plus s equals n, then certainly those are all going to be the coefficients on x to the n. And so now we're getting somewhere. Right now we're getting somewhere because we can instead write this. We're ranging over n, still in the first sum, and the second sum, so the coefficient will be the sum ranging from r equals 0 up to n of n choose r, a to the r, b to the s. And the reason for this, and then we need to multiply by an added n factorial. Now the reason for this is because the denominators, r factorial and s factorial, it doesn't quite look like n choose k. I mean, it looks really close, right? Because the denominators, in n choose k, like n, the denominator is k and n minus k. They add up to n, okay? And that's exactly what's happening here. The denominators are adding up to some fixed number. And now we're going to turn this into n choose r by, well, we don't have an n factorial in the numerator, So we're going to have to divide that out at the end, but we actually want that to happen, and we want that to happen because we want this to be an exponential generating function for something. And in fact, this is the exponential generating function for this sequence right here. And that actually matches exactly what the rule 3 says. So that concludes this part, and that's the last of the rules. The next video is going to describe one lengthy example that kind of puts all of this together and introduces the Catalan numbers.